Let's do an example of using the pumping lemma for regular languages to show that a language is not regular. So this is the language we're going to look at. The language is A, and it's the set of strings 0 to the n, 1 to the n, 2 to the n, such that n is greater than or equal to 0. So it's a string of zeros, ones, and twos in that order, where the number of zeros is equal to the number of ones, which is equal to the number of twos. And we'll actually do two ways to do this, one of which is much, much easier. So I'll show that one first. So we're going to assume that A is regular. That's the first part of the proof. Okay, and then we're going to state that P is the pumping length. Again, we may not know exactly what P is, but if A is regular, then it has a pumping length, and we're calling that P. So now we need to choose a string S. And the string that we choose has to be at least as long as P. So let's choose 0 to the P, 1 to the P, 2 to the P. Okay, that's going to be S. Okay, so that we have length of S is greater than or equal to P. We've satisfied that condition. And we'll see in a minute why this is a good choice. Oh, and we also have S as an element of A. These you don't necessarily have to state in the proof. It's obvious by looking at them, but it's a good practice to state it to yourself. Because again, if you try to pump a string that's not in the language and end up with a string that's not in the language, you haven't proved anything. So you have to make sure that S is actually in the language you're trying to prove is not pumpable. Okay, so we have this S. Now remember the two conditions that we have on our decompositions. So condition number 1 is that the length of Y has to be greater than 0. Okay, so we cannot choose a decomposition where Y, where the middle bit, the middle piece, I shouldn't use the word bit, where the middle piece is actually empty. We can't do that. And we also have, oops, can I fix that? Yeah. And we also have that the length of X and Y has to be less than or equal to P. Okay, so these parts can't be too long. So what possible decompositions do we have? This restriction in this case is actually very restrictive. Okay, so we have 0 to the P, 2 to the P. And somehow we need to get chunks that are X, Y, and Z. Well, the total length of the first two parts can't be any bigger than P. So if I start from the left here and I start working right to assign X and Y, so some part here is X, where can Y be? Well, Y can't go past the zeros. Okay, why am I saying that? Because this total length has to be less than or equal to P. So I can't shift Y any further to the right. Because if I did, if Y was in the ones, it would mean that X and Y covered all of the zeros and some of the ones. That's what that would mean. And if that was true, they have length P just from the zeros, and then they have additional length from however many ones Y is covering. Okay? So actually, X and Y must be in the zeros, and that leaves this piece to be Z. This bit here. Okay, if I ever say bit, I'm not saying bit as in the computer science sense, I'm saying. Okay. So there are our possible decompositions. Now within that, you can argue that there are many more decompositions. So real quick, if length of xy is less than or equal to p, and note here, since it's less than or equal to p, z actually could be over to the left. Z could actually encompass some zeros as well. Okay? And we'll see in a minute why that doesn't really matter. But we'll be really precise. So if the length of x and y has to be less than or equal to p, you could argue that x could be p minus 1 and y could be 1. Or x could be p minus 2 and y could be 2. Or x could be p minus 3 and y could be 3. Or x could be, the length of x could be 0 and the length of y could be p. So what I'm saying here is that actually, while there's a finite number of decompositions, there are many more decompositions. We don't want to handle each one of those in an enumerative case-by-case fashion, okay, because we don't actually know what p is, right? So while it is actually finite, we can't list it, right? And we wouldn't want to anyway. That gets way too long to do. So what we're actually going to do is say that they have some variable length. Okay, so we're going to say that the length of y is equal to m. Okay, so it could be 1, could be 2, could be p, but it's going to be m. All right, so then what does our decomposition actually look like? The x piece, oh, and I'm also going to give you another one. I'm going to tell you that the length of z is going to be equal to, I don't want to use n, we've used n before, let's call that k. Okay, so the x piece is going to be all of the zeros from the beginning that aren't covered by y or z. So it's all of the zeros, p minus m minus k. So if I take the p zeros and I give m of them to y and k of them to z, then x is going to be the ones left over. It's going to be p minus m minus k. Okay, and then the y piece is going to be 0 to the m. Okay, there's m zeros. The z piece is going to be the rest. It's going to be 0 to the k, 1 to the p, 2 to the p. Okay, so if we add this back in, I've got p minus m minus k zeros plus m zeros plus k zeros. So I still have p zeros. I haven't actually done any magic and lost part of the string. All of my string is still there. Okay, so let me just transfer this to a new sheet. Okay, so now we argue that this is really the only possible decomposition. Okay, there are a number of decompositions in here based on which values we choose for m, p, and k. Yeah, for m, p, and k, but they're all handled here. Okay, so now what are we going to do? Well, now we're going to pump y. And we need to pump y in such a way that we end up with a string that's not in the language. That's the end game here. So, how can we pump y? There's two ways to do it. You can pick either one. I'm going to do both. I can pump down. Okay, so if I let I be 0, what is my resulting string? I'm going to have my x bit still, because x doesn't get pumped, which is p minus m minus k. My y bit is now gone. Okay, I said repeat y 0 times, which the repetition actually means how many times does y appear. It doesn't mean duplicate. Okay, so it's appearing 0 times. So the y piece is gone. And now the z piece is 0 to the k, 1 to the p, 2 to the p. Okay, and this is actually equal to 0 to the p minus m, 1 to the p, 2 to the p. Okay, so really what we did is we just removed the y piece. We showed that we could remove the y piece. How do we know that this string is not in the language? This requires just a little extra thought. So we're asking this question: is p minus m equal to p? It is if m is 0. Can m be 0? No. We have the condition length of y must be greater than 0. And what was the length of y? M. M has to be greater than 0. If m is 1, p minus 1 is not equal to p. If m is 1,000,000, p minus 1,000,000 is definitely not equal to p. Okay? So here, by pumping down, we show that the string we get, this string is not in A. All of the strings in A had the same number of 0s, 1s, and 2s in that order. So this string is not in A. We could have also chosen to pump up. Notice you never want to pump with I equals 1. That's not going to do anything for you. You're going to end up with the same string again. Okay? But because we have to show that for each decomposition there is some I that makes the resulting pump string out of the language, we only really have to find one. I have to find one I. So I found one, but let's do another one, just so we can make sure we see how this is working. All right, so if I let I be 2, what do I get? Here's my x piece. Here, I'll do it long ways. So here was my first y. Here's my second one. What? Oh, just kidding. Okay, so my first y is here, my second y is here, and then here's my z piece. Okay, so what is this really? This is equal to 0 to the p minus m minus k, 0 to the 2m, I'm doing this long, 0 to the k, 1 to the p, 2 to the p, it's a p. Okay, and then what is that? If I take p minus m plus 2m minus k plus k, so these guys go away, this guy goes away, and I really end up with 0 to the p plus m, 1 to the p, 2 to the p. Okay, you don't have to necessarily usually in your proof show all of these steps. I'm just showing you how I would go about figuring out what is my resulting string. Okay, so again, we can actually more intuitively see what's going on if we consider that what did I do? The length of y was m, and I pumped it so that it's appearing 2 times. Okay, so I get an extra m. All right, y appears 1 time in the original string, it appears 2 times in the pump string, so I have m more zeros. So now I have a number of zeros that is strictly more than the number of 1s and 2s. Again, why do I know it's strictly more? Y can't be 0. I'm sorry, m can't be 0. The length of y can't be 0. So p plus m is definitely not equal to p. Okay, so this is not an A. So what do we have? To finish off our proof, we would say that for every decomposition, and here's the decompositions, this is what we did here, these are the decompositions. For every one of them, I can find an I, and here in my proof I would choose to use either I equals 0 or I equals 2. I don't need to show both. I just need to say I found an I such that x, y to the I, z is not an A. Okay? So then we can conclude that this string is not pumpable, and then we can conclude that A is not regular. So that finishes our proof. I also said that I would show you a harder way to do this. Okay, why would you want a harder way? Well, you don't. You don't ever want to try to find a hard way to do it. But let's say it didn't occur to you right away that 0 to the p, 1 to the p, 2 to the p would be a good string to use. Then you might have chosen a different string. And it might still be possible that that string can't be pumped, or that when you pump it you get a resulting string that's not in the language. So let's do one of those. The string we're going to choose is 0 to the p divided by 3. 1 to the p divided by 3. 2 to the p divided by 3. Okay, so when I add up all of my 0s, 1s, and 2s, I do have, so this is s, get my variables declared. So I do have that the length of s is equal to p. Right? Yes. Okay, so this is a valid string to pump. It meets the condition that it's at least as big as the pumping length. So I can attempt to pump it, and if I can show that it's not, that after pumping the resulting string is not in the language, then I win. So that's what I want to do. And I also know that this is, so I've met that condition, and it's in the language. Okay. So I've met both of these conditions. What gets challenging here is considering all of the decompositions that are possible. Before, what forced our decomposition was the choice of the string. So sometimes it's nice to think of this as a game that you're playing with an adversary. So you get to pick the string. Why do you get to pick the string? Because the pumping lemma says that for every string in the language, it's pumpable. So you can pick any one you want. However, the pumping lemma also says that for every decomposition, okay, so your adversary gets to pick the decomposition. This is why we have to show all of the decompositions. After we've shown the string, we have to show that no matter which decomposition your adversary picks, you can show that there is some I for which the resulting string is not in the language. So we have to actually show all of the decompositions. If we can force the number of decompositions, the ways that it can be decomposed to be simple, then our job is simpler. Sometimes we can't do that. Sometimes we have to do a very enumerative case-by-case proof, and that's what we're going to do here. So, what can my decomposition look like? Again, I'm going to remind ourselves over here, length of y has to be greater than 0, and length of xy has to be no bigger than p. Well, the whole string is p. This means that x and y could, in fact, be the entire string. Okay, so now we need to show all of the decompositions. So let's say, because the length of x and y has to be less than p, let's just say that x is all zeros and y is located in the zeros only. Okay? If we do that, so we're going to call it case 1a, y is all zeros. I shouldn't say all zeros. I don't actually mean it's all of the zeros. I mean y is composed only of zeros. So let me say that more clearly. y is composed only of zeros. Okay, if I do this, z may be present in the zeros as well, just like, and then in that case, it's really like this case. Okay, see here, if x is all in the zeros and y is all contained in the zeros, z could start at 1 or z could be in the zeros as well. We don't need to restrict that. Either one of those cases is possible. However, in this case, our pump string is going to end up being 0 to the p minus m, 1 to the p, 2 to the p, if I equals 0, and m is the length of y. Okay, we've already proved this. All right, so you can look back and see how we did that, but this is the resulting string that we're going to get. Okay, I'm going to call the next case 1b. What's my next case? X could be all of the zeros and then possibly some of the ones. Okay, y could be contained entirely in the ones, and z could be all of the 2's and then possibly some of the 1's. So let me see if I can make that. So what I'm really saying is y is composed only of 1's. This is what I'm saying. And what I'm saying is I'm going to again use, so as a running example, let me just put these here. Length of y equals m, length of z equals k. Okay, so when I say m and k, you know what I mean. All right, so this is x, and then x could also be 1p divided by 3 minus m minus k. So this bit is x. This bit is y. Oops, I'm forgetting a piece. Oh, is that what I meant? You know what? I'm actually saying something that's not what I mean. What I actually mean is this. Okay, what I meant to say was that the number of ones in z is k. That's what I meant to say. So let me very quickly go back and change. Did I actually say that out loud last time? I did. Horrible. Okay. This is what I meant here. So in case this was confusing to you when I was saying this before, this is what I mean. I mean that z is composed of k zeros and then p1s and p2s. That's what I meant. Sorry. Okay. All right. So here's my decomposition. And note here that k could be 0 and m could be p divided by 3. So y could contain all of the ones, or y could contain only some of the ones, with some of the ones also being contained in x or contained in z. All right, this covers every possibility of those. All right, so if y is composed only of ones, how do we get this string out of the language? That we're going to do the exact same thing that we did in case 1a. We're going to set I equal to 0. If I equals 0, then we end up with, did I really do that? Sorry guys, hold on. still thinking of my last example. I shouldn't have referred to my last example there. I should have... Okay, hold on. P divided by 3 minus m. 1 to the p divided by 3. 2 to the p divided by 3. This is what I'm trying to say. Okay, so back to case 1b. Y is composed only of ones. I'm going to set I equals 0, so I'm effectively removing the y piece. Okay, and then what do I end up with? I end with 0 to the p divided by 3, 1 to the p divided by 3 minus m, 2 to the p divided by 3. Okay. So it really looks the same as case 1a. It's just which number is losing some so that they don't all have the same number of this character, right? Okay. Yes. Yep. Okay. So let's go to case 1c. Okay, and what is this one going to be? Y is going to consist only of 2's. Okay, so again, we're going to have 0 to the p divided by 3. This is the x bit. Also included in the x bit is this part. This is x. And x could have some number of 2's. We don't know. Okay, so note here that z could be, length of z could be 0, k could be equal to 0, and m could be p divided by 3, that could be the size of m, or m could be some value from 1 up to p divided by 3. Okay, and so when we do this, we're going to have the same, for the same argument, we're going to end up with something similar to what we've had in the other case 1s. So we're going to end up with p divided by 3, 1 to p divided by 3, 2 to p divided by 3 minus m, if I is 0. So when I is 0, when the string is pumped down, I end up with a string that's not in the language. Okay, so this is actually the easier cases to handle here. When y is contained all in one character. So let's go to the next case. So case 2, and you notice I could have simplified this considerably with just an argument, but we're trying to be very precise and we're trying to show exactly what's happening. Okay, so that's why this might seem a little bit long. I want to make sure that it's absolutely convincing that every decomposition is covered and that every decomposition will result in a string pumped out of the language. That's what I'm trying to do here. Okay, so case 2 is going to be okay, let me actually say symbols. Symbols is probably the better term. Okay, so y is composed of some 2 symbols, and then we're going to break this down. So 2a is y is composed of zeros and ones. What we're saying is that y could lie across the boundary between 0 and 1. It could have some zeros and some ones in it. Okay, so what does our string decomposition look like here? Looks like 0, p to the 3 minus. Okay, how do we handle this? We're going to introduce some new variables. Let's let, and I don't want to use x, y, and z. I don't want to use m or k. Eventually I'm going to run out of letters. Let's use a and b. Okay, so let's let the length of y equal a plus b. Okay, so length of y is a plus b. What I'm going to use is I'm going to say that y contains a zeros and b ones. That's what I'm saying here. Okay, so how many, so x is going to contain the p divided by 3 minus a zeros, minus the ones that are in y. Y is going to contain a zeros. It's also going to contain b ones. Okay. Z, I'm thinking and saying and writing what I'm thinking and saying and not what I mean to. Okay. Z could also contain some ones. Okay, we haven't restricted that actually. So these are going to be the ones that are in Z. And then Z also now has to cover all of the 2's. Oh, let's do this easier. This is going to make it easier. Okay. Z can just contain the p minus 3 ones that are not in y. That's easier. P divided by 3. P divided by 3. All right. So, what piece is x? This is x. What piece is y? This piece is y. And this piece is z. Okay. We note here y could in fact be all of the zeros and all of the ones. That hasn't been restricted, right? Because we don't have any restrictions on x and z other than that the length of x and y must be less than or equal to p, and since the entire string is less than or equal to p, that means we really don't have any real restrictions on x. It could be epsilon. Okay, x and y, x and z could be epsilon. All right, so here's our decomposition. What are we going to do? Well, we could do what we did before in pump down. That would absolutely work. What happens if I pump down? This bit goes away. And I'm left with p divided by 3 minus a zeros, p divided by 3 minus b ones, and p divided by 3 2's. Okay, when is it the case that p divided by 3 minus a is not equal to p divided by 3? If a is at least 1, right? And we know because the length of y has to be at least 1 that either a or b is at least 1. So either it's the case that the number of zeros is not equal to the number of 2's. So same thing here. Okay. That's when these will not be an inequality, right? So I know at least that the number of zeros is not equal to the number of 2's, or the number of ones is not equal to the number of 2's. It could also be the case that both a and b are at least 1, and then the number of zeros and the number of ones is not equal to the number of 2's. Okay? So that's possible. Actually, based on, so to clarify, because I've already handled the case that y is only contained in zeros or y is only contained in ones, it's actually true that both a and b have to be at least 1. Okay, so let me put this in here. B is greater than or equal to 1 and a is greater than or equal to 1. So this is actually true. Up here, all of these cases 1a, the cases 1a and 1b are what happened when y was either just zeros or just ones. So a and b both have to be non-zero in order for this to be a new case. Otherwise, I'm just repeating an old case. Okay? So now I do know for a fact that the number of zeros and the number of ones, that these are not equal to the number of 2's. Okay, so that's one way that I could do this. I'm also going to show you the other way, but I need a new page to do that. So let me rewrite my string. Oops. Oops. Well, that's really not clear, is it? That's a little better. Okay, so there's my string. What if I let I equal 2? I'm going to repeat y. That's what I'm going to do. So what do I end up with? There's my first repetition, or my first appearance. It's probably better. There's my second one. Hopefully I wrote that all correct. Looks good. Okay, so what does this actually mean? It actually means this. Let me add those back in. Let me add that back in. What did I end up with? 0 to the p divided by 3, 1 to the b, 0 to the a, 1 to the p divided by 3, 2 to the p divided by 3. Okay, this is not in the language for the pure reason that these are out of order. Okay, so this is not in A. All right, case 2b, I'm actually not going to draw it out for you, but what is it? It's y consists of, let's give this actual variable names, a ones and b twos. Okay, y consists of a ones and b twos. What I mean is y is lying on the boundary between 1 and 2. Okay, what's going to happen if I pump down? I'm going to get something that looks a lot like this, okay, but just shift it over onto the other boundary. And if I pump up, let's just say I pumped up, what do I end up with? I end up with 0 to the p divided by 3. I'm going to get oh, maybe we should draw it out because I'm drawing a blank. What am I going to get? I'm going to get an extra, yeah, I'm going to get 1 to the p divided by 3, and then I'm immediately going to have 2 to the b, 1 to the a, 2 to the p divided by 3. Okay, that's what I'm going to end up with. Okay, when I go ahead and repeat this bit, I end up with this out of order. Okay, and this is not an element of A. It might be a good exercise to go through the steps we took in 2A to convince yourself that this works. Okay, that we're actually going to see this out of order repetition happening between the 1s and the 2s. Okay, so that's case 2. And case 2 is y is composed of some 2 symbols. And then we have it's either composed of zeros and ones or ones and twos. Why can't it be zeros and twos? Because all of the symbols in Y have to be directly adjacent to each other. We can't just pick and choose chunks out of the string. It has to be a sequential number of symbols that are next to each other. Okay, so that's why there's only two cases in case 2. There's 2A and 2B. All right, so we actually have one more case here to cover because of the string that we chose. What's the string? What's case 3? Let's remind ourselves the string we chose: 0, p divided by 3, 1, p divided by 3. Excuse me. 2, p divided by 3. And what do we need? We need the length of y to be at least 0, to be at least 1, to be greater than 0, and we need the length of xy to be no bigger than p. Because the length of our string is equal to p, this will always hold for any decomposition into x, y, z. Okay, because I can take the entire string to be x and y. I can also, because there's no restriction on x to not be empty, right? The only thing we were restricting was y. We never restricted x or z to not be empty. Y could be the entire string. Okay? So our third case would actually be y is composed of, we're going to say, some number of all 3 symbols. Okay, we have to consider what happens if y spans the whole string, or maybe just there's a little x on the left and there's a little z on the right, and so y actually has zeros, ones, and twos in it. Okay, what happens then? If that happens, there's 2 things that we can do. So how do we want to write this? We're going to let, yeah, let's do that. Let's use A for the number of zeros that's in y. Y would have to contain all of the ones, okay? Because that's what we're talking about. If y contains zeros and twos, then it has to contain all of the ones. And let's let b be the number of twos that y contains, and that means z could contain the rest of them. What did I call it? B. There we go. Okay, so this is x. This is y. This is z. Okay? So now what do we do? We need to find an I for which this is not in the string, not for which the resulting string is not in language, right? Well, what if we take I equal to 0? There's actually a problem with that, okay? But let's think about it first. Let's let I equal 0. Okay, so what I'm really saying is wipe out y. Okay, so I end up with 0 to the p divided by 3 minus a, 2 to the p divided by 3 minus b. Okay, so it looks here like all of my 1s are gone. I have the same number of zeros and 2s, but all of my 1s are gone. So why am I saying that this is a problem? Well, what if a is equal to p divided by 3 is equal to b? Okay? We did say y could be the entire string. It doesn't violate any conditions for y to be the entire string. If y is the entire string, then a is p divided by 3 and b is p divided by 3. Okay? If that's true, what actually is this? This is 0 to the 0, 1 to the 0, 2 to the 0. And why is that a problem? What was our definition? 0 to the n, 1 to the n, 2 to the n, such that n is greater than or equal to 0. Okay, that means I could have no zeros, no ones, no twos. I could have the empty string. The empty string is an element of this language. That's what I have here. This is the empty string. That means this is an element of A. Okay? So this means I have not succeeded in pumping this out of the language. Okay? So we need to take a different approach. One that's been successful before has been pumping up. So let's try that. Let's let I be equal to 2. Okay, so we're going to do this slightly the long way. We're going to have 0 p divided by 3 minus a, our first occurrence of y, our second occurrence of y, and z. Okay, are we convinced that that's all in there? This is x, this is y, this is y, and this is z. Right? Okay, so let's clean it up. When these are next to each other, they get added back together. These are next to each other, they get added back together. So maybe I can here write it more cleanly, maybe. What do I actually have? I have 0 p divided by 3, 1 p divided by 3, 2 to the b. Well, we've already failed, but let's keep writing. 0 to the a, 1 to the p divided by 3, 2 to the p divided by 3. Okay, did I get it all? 0 to the p divided by 3, 1 to the p divided by 3, 2 to the b, 0 to the a, 1 to the p divided by 3, 2 to the p. Okay, yep, it's all there. All right. So, why do we know that the string is not in the language? We have, obviously, all of our symbols are not occurring in the proper order. They're supposed to be 0, 1, 2. Bam, done. Okay, that's it. That's the language. We also know that, so even if B and A were, in fact, 0, we would have a problem here, because we'd have 0, p divided by 3, 1 p divided by 3, 1 p divided by 3, 2 p divided by 3. Okay, so no matter what, we have a problem. We've said in the case that y is composed of some number of all 3 symbols, so this actually implies that A is strictly greater than 0 and B is strictly greater than 0. Okay, so I definitely have something there. Okay, so this is not an element of the language. All right, and I claim that that covers all the cases, right? We thought about if y is only one symbol, and then we've laid out if it's 0, if it's 1, if it's 2. Okay, that's all of the cases if y is only 1, 0. If y is only one symbol, there's only 3 possible symbols it could be, and we've given all of those cases. We've also thought about if y is 2 symbols. Well, then it could be 0 and 1. Some number of zeros and some number of ones could span the boundary between 0 and 1. Or it could be 1s and 2s. It could span the boundary between 1 and 2. And we laid out those 2 cases. And then the last case, y, has some number of every symbol, all 3 symbols in it. And now we've covered all of these cases. And for each case, we found some I. So here, I'm actually going to cross this guy out, because this failed, right? So for each case, we found some I, so that once we pumped it, the resulting string was not in language. Okay? This shows The language is not pumpable, and if the language is not pumpable, it can't be regular. So we've actually proved that this language is not regular.